Imagine a pipeline you cannot see. No steel running across deserts, no valves, no compressor stations, no visible infrastructure stretching across continents. And yet this invisible pipeline is already being built. It is quietly connecting renewable power plants to industrial clusters, ports, chemical facilities, and global trade routes. It does not carry oil, it does not carry natural gas, it carries something far more complex. A system of electrons, molecules, contracts, logistics, and capital that together form the foundation of the green hydrogen economy. And at the center of this invisible system are three companies operating in different layers of the same machine: Linde plc, Shell plc, and Siemens Energy. At first glance, these companies appear to be doing different things. One builds industrial gas infrastructure, one develops energy projects and global fuel networks. One manufactures complex energy systems like electrolyzers and grid equipment. But if you zoom out and look at the system as a whole, something surprising begins to emerge. They are not competing in the traditional sense. They are wiring different layers of the same invisible pipeline. To understand this, you have to start with a simple question. What does it actually take to move green hydrogen from renewable electricity to real industrial use? Not in theory, not in a lab. But in the real world, where factories need reliability, investors need returns, and infrastructure must operate continuously under stress. The journey begins with renewable electricity: solar farms in the Middle East, wind farms in the North Sea, hybrid renewable parks in Australia and Chile. These assets generate electrons, but electrons alone are not enough. Electricity cannot easily be shipped across oceans or stored for long periods at industrial scale. This is where the system makes its first transformation. Electricity becomes hydrogen through electrolysis. This is where Siemens Energy enters the picture. The company is not just selling electrolyzers. It is building the front-end conversion layer of the invisible pipeline. Electrolyzers take water and split it into hydrogen and oxygen using electricity. But in reality, this is not a simple process. It requires stable power input, water treatment systems, thermal management, power electronics, and integration with fluctuating renewable energy sources. The electrolyzer is not a standalone machine. It is part of a tightly coupled system that must operate within narrow performance windows. And here's where the first hidden constraint appears. Electrolyzers do not like variability. Renewable energy is inherently variable. When wind drops or clouds pass, the system must either ramp down or compensate. This creates a utilization problem. If the electrolyzer is not running at high capacity, the cost per kilogram of hydrogen increases dramatically. This is one of the first cracks in the invisible pipeline. But let's assume hydrogen is successfully produced. The next question is even more challenging: how do you move it? Hydrogen is not like oil. It is the smallest molecule in the universe. It leaks easily, it embrittles metals, it has low volumetric energy density. Moving hydrogen at scale is not just a transportation problem. It is a materials science problem, a compression problem, a storage problem, and a safety problem all at once. This is where Linde plc becomes critical. Linde operates one of the most sophisticated industrial gas networks in the world. Long before green hydrogen became a buzzword, Linde was already moving hydrogen for refineries and chemical plants. But what it is doing now is fundamentally different. It is extending its expertise into a new kind of network, one that must connect decentralized renewable production with distributed industrial demand. Linde is effectively building the middle layer of the invisible pipeline. Liquefaction plants, compression systems, storage tanks, distribution logistics. These are the physical components that allow hydrogen to move from where it is produced to where it is needed. But the challenge is scale. Moving hydrogen locally is one thing. Moving it globally is another. At this point, the system faces a fork. You can either move hydrogen as a gas, which is expensive and limited in distance, or you can convert it into something else. Ammonia, liquid hydrogen, synthetic fuels. Each option introduces new complexity, new infrastructure, and new losses. And this is where Shell plc steps into the system. Shell is not just investing in hydrogen production. It is positioning itself as the orchestrator of global energy flows. Ports, shipping routes, trading desks, and downstream distribution networks. This is where Shell has a structural advantage. Shell understands something fundamental about the invisible pipeline. It is not just a physical system, it is a commercial system. Hydrogen does not move unless there is a buyer. Infrastructure does not get built unless there is long-term demand. And demand does not materialize unless pricing is competitive and reliable. This creates a circular dependency. Producers need buyers. Buyers need supply certainty. Infrastructure needs both. Breaking this loop is one of the hardest challenges in the entire hydrogen economy. So what Shell is doing is quietly building demand anchors, industrial customers, shipping fuel agreements, refueling networks. By locking in off-take agreements, Shell effectively creates pull through the system. This pull justifies investment in production and infrastructure upstream. Now step back and look at the system again. Siemens Energy converts electrons into molecules. Linde moves and stores those molecules. Shell creates the demand and distribution networks that make the entire system economically viable. This is the invisible pipeline. But here's where the story becomes more interesting. Because this pipeline is not smooth, it is under constant stress. Consider utilization. If renewable power fluctuates, electrolyzers operate below optimal levels. If hydrogen supply is inconsistent, industrial users cannot rely on it. If demand is uncertain, infrastructure sits idle. Every layer of the system is sensitive to the performance of every other layer. Now consider cost. The target that keeps appearing in industry discussions is $2 per kilogram of hydrogen. This is not an arbitrary number. It is the threshold at which hydrogen begins to compete with fossil fuels in many applications. But reaching this number requires everything in the system to work almost perfectly. High electrolyzer utilization, low-cost renewable electricity, efficient logistics, strong demand, favorable financing conditions. Remove any one of these elements and the economics begin to break. And this is where the invisible pipeline reveals its true nature. It is not a single system, it is a chain of interdependent systems, each with its own failure modes. If Siemens Energy's electrolyzers cannot maintain high uptime under variable conditions, production costs rise. If Linde's infrastructure cannot scale efficiently, transport costs increase. If Shell cannot secure long-term demand, projects stall before reaching final investment decision. This is why so many green hydrogen projects struggle, not because the technology does not work, but because the system does not align. Now imagine a scenario where subsidies begin to decline. This is not hypothetical. Policy support is already evolving in different regions. If subsidies drop, the system must stand on its own economics. This is the ultimate stress test. In that world, only certain configurations of the invisible pipeline survive. Projects with high utilization rates, regions with cheap and abundant renewable energy, industrial clusters where demand is concentrated, companies with low cost of capital and integrated capabilities. This is where competitive edge becomes critical. Linde's edge lies in its operational expertise in existing industrial gas networks. Siemens Energy's edge lies in its ability to integrate complex energy systems at scale. Shell's edge lies in its global trading and distribution capabilities. But even these advantages are not guaranteed under stress. If utilization drops, even the best electrolyzer struggles. If demand weakens, even the most advanced logistics network sits idle. If financing tightens, even large companies delay investments. So the question is not whether the invisible pipeline exists. It clearly does. The question is which version of this pipeline survives under real-world conditions. Now take this one step further. This invisible pipeline is not being built in isolation. It is colliding with other systems. The electrical grid, data centers, electric vehicles, industrial electrification. All of these systems are competing for the same renewable energy resources. If electricity demand rises faster than supply, hydrogen production becomes more expensive. If grids become constrained, projects face delays. If alternative decarbonization pathways become cheaper, hydrogen demand weakens. This is the system under stress. And yet, despite all of these challenges, the invisible pipeline continues to expand. New projects are announced, new partnerships are formed, new infrastructure is planned. Why? Because at a systems level, hydrogen solves a problem that few other technologies can address. It provides a way to move renewable energy across time and space. It enables decarbonization of industries that cannot easily electrify. It connects energy systems to chemical value chains. But solving a problem does not guarantee success. Execution does. And this is where most of the story is hidden. Not in the announcements, not in the headlines, but in the details of how these systems are actually built, financed, and operated. If you want to understand where this is going, you have to think like an investigator. Follow the molecule. From renewable electricity to electrolysis. From hydrogen production to storage. From storage to transport. From transport to industrial use. At each step, ask the same question. What could break? Because the future of the green hydrogen economy will not be decided by who builds the biggest projects. It will be decided by who builds systems that survive stress. And this is exactly where H2 Hub by Linde Energy becomes critical. If you are a developer, consultant, or investor trying to understand how to navigate this system, you need more than high-level concepts. You need tools, models, and real-world execution frameworks. H2 Hub is designed to help you break down these complex systems, understand the economics, and build projects that can actually reach financial close and operate successfully. Because in the end, the invisible pipeline is not just about technology. It is about alignment. Alignment between energy, infrastructure, capital, and demand. And that alignment is what separates projects that get announced from projects that actually get built. So the next time you hear about a new green hydrogen project, look beyond the headline. Ask where it fits in the invisible pipeline. Ask how each layer connects. Ask what happens when the system is under pressure. Because what is being built right now is not just a new fuel, it is a new global system. And like all systems, it will reveal its strengths and its weaknesses only when it is tested.